thank you all for coming. I appreciate you being here. A couple notes real quickly. There's a lot of information in the slides, and some of it will go quickly. The slides are all going to be available to you afterwards, so don't worry too much if things seem to go fast. I want to make sure that I don't run over into the next speaker's time. What I'm here to talk to you about is, okay, there we go, is some of the work I've been doing for the past 5 years, and I'll give you a little bit of history of that work. Very brief introduction to LORD, but we have a booth here today, so I won't say too much about that. I invite you to speak to anyone sitting in the back or standing in the back with the red or a white shirt on and a LORD logo about that, and then come see us. And then we'll talk specifically about some of the work we have done and the benefits that we're seeing in thermal management in electric motors by potting the end windings, and do some of our own tests and then external tests that we've done with customers when we are able to share that data. We've done, of course, information that we can't share, but I'll share as much as I can. The final couple slides will be just some thoughts about what we feel like we've learned about motor potting over the past 5 years, some things that help make it easier to pot the motor, that make the thermal transfer better, that will help you get the optimum benefit, and some considerations when you're trying to figure out whether you want to use a silicone or an epoxy. So this is our one-slide introduction. LORD is a 90-year-old company. We are privately held. We're technology and manufacturing. 50% of our company is mechanical devices for vibration and motion control, passive or active kinds of devices, and sensing systems to go along with that as well. The other half, which our team here at this show is representing, is the chemical side, and that's the electronic materials specifically for and thermal management even more specifically. The LORD CoolTherm brand was introduced last fall to emphasize and call out the products that we are using in power electronics motors that have high thermal conductivity and that will allow you to improve power density in all sorts of different kinds of devices. Particularly today, we're going to be talking, I don't know if you can even see, there's supposed to be a green dot, but if you can't see it, I won't even try to point at things anymore. I think you can't see it in the back. So there are different forms of materials that we can provide or that you can find. We are specifically in this session going to focus on potting materials. Potting materials are low viscosity materials. They're two-part, so there's a resin and a hardener. You mix them together and they begin to cure over some amount of time. They are low viscosity. They self-level, which means when you pour it in, they will fill in all the nooks and crannies and kind of level out. Depending on the chemistry you choose, they can be rigid or they can be soft. They can have high chemical resistance, a lot of different kinds of properties there. And it's specifically what we're looking at today is going to be getting heat away from the hot components and getting it out to the heat sink. Tomorrow during the EV Momentum, my colleague, Dr. Wolfgang Werner, will be talking about the adhesives, gap fillers, sort of a more general thing. So I'm going to skip over that for today. But in general, we have different ways of dispensing the material. It has different flow properties, and we can try to apply different materials in different applications. The other thing is that we have different chemistries that are possible. So silicones, urethanes, epoxies, even acrylics for some of the adhesives. What we're going to be talking about is thermal benefit in motors, and it turns out that the thermal benefit that you get doesn't have anything to do with the chemistry. It has to do with the thermal conductivity of the material. So if it's properly applied and it's got good adhesion, then you should get the same thermal benefit. The different chemistry that you choose depends on other aspects. Do you need something that's more rigid? Do you need something that's softer? Do you need chemical resistance or moisture resistance? Talk about that more later. This is an eye chart that I do not expect you to know. That's what we're for. You're motor designers and motor experts. We are materials experts. That's why we want you to talk to us, work with us, so that we can select the best material for your needs. So on to the motor potting studies themselves. Just about 5 years ago this month, LORD was made aware of the potential benefits of potting motors with high thermal conductivity materials. Dr. Shafig Nateg, who is actually sitting not too far from me right now, was a student at KTH in Sweden at the time. And he had become aware of a thermally conductive silicone that Lord made for power electronics called SC320. SE stands for silicone. It's a 3 watt per meter K thermally conductive electrically insulating material. And what he did was essentially encapsulate the end windings and the slots with the SC320 and compared that to a motor that had just been varnished and to a motor that had been potted with an epoxy with about 1 watt per meter K. And the 3 different graphs you see show that. And what's being measured there is the end winding temperature in this particular motor. You can see from the design, this is actually cooled by liquid in the housing of the stator. And so what's shown is the temperature of the unpotted motor as the top curve at several different currents until it reaches its power limit. Those same conditions when you operate motors that are potted are lower temperature. And so with the epoxy light, you can see you get about 50% of the benefit. That's a 1 watt material. But if you have a more thermally conductive material, a 3 watt material, you can get temperature reductions up to about 50 degrees C, depending on the power. And if you go to the temperature limit for each motor, the power increase that you get out of that was about 26% higher with the 3 watt material. When we first heard about this, I knew nothing about motors, but we thought that sounded like a pretty big number. So we started engaging with customers and talking to people and seeing, is this something that would be interesting? And these are the benefits that we would have expected as we talk to different manufacturers. Higher power density. So for the same size motor, you can get more power out of that motor. Or better reliability. So when you put the material in and you get much, much lower temperature, 30 to 50 degrees lower temperature, every 10 degrees that you lower the temperature, you're doubling the lifetime of the motor. So a 30-degree lower temperature is a substantial increase in the operating life. You also get lower copper losses in the stator, and if that's a primary source of issue for you, then that's important, but it turns out that that's less of a benefit than the improvements in power density and lifetime for most of our customers. Being engineers, we wanted to see if we could reproduce this data ourselves. So we did a less sophisticated study. We purchased 3 motors that were off the shelf. So the description is here, Class F 155C motors, NEMA premium efficiency, 3 horsepower, totally enclosed, fan cooled. So the cooling was from a fan blowing air outside of the housing. And we did heat tests on these motors in 3 different conditions. As we received them, no potting at all, but they do have varnish on them. Potted with a 3.2 watt silicone, the same Cooltherm SC320 material. And because these were varnished, we do not think that we penetrated the windings very efficiently with any of the potting materials. So we're essentially potting over and making a connection between the housing of the motor and the windings. And that's really the critical thing, is to make that connection, to fill in those gaps between the windings and the housing and make good contact there. But for comparison, we used a standard epoxy 1.4 watt that was used in the industry. We did this work in conjunction with Dr. Keith Klontz at Advanced Motor Tech, because as I said, we really didn't know much about motors, so we were depending on someone who knew motors to help us understand how to do these studies. This shows how the potting is done. In this case, it's quite simple. You put an insert in the middle to keep material out from the space where the rotor will go. You put a seal at the bottom and make sure that material doesn't leak out the bottom. Silicones, you generally want to dispense at room temperature, so you mix the A and B parts together and just pour them in. This motor in particular had some large gaps between the stator and the housing, so it was very easy for the material to flow all the way down to the bottom of the motor. So you could do a very easy top fill of this motor. You put that in vacuum just to get out sort of the larger air bubbles. Again, like I mentioned, we're not expecting to penetrate the windings, so you don't need extremely high vacuum in this case. And then cure it up. Silicones will generally cure at room temperature overnight, and that's the way this one was done. You often will get better adhesion if you do an elevated temperature cure. 85 to 125 C for an hour or two. The heat test was then run on each of these three motors using these conditions where they were run essentially at the rated horsepower of the motor and then 163 and 174%. What we were trying to do was reach the temperature limit of the unpotted motor and then see how everything looked, how the temperatures looked for the potted motors. I should mention the placement of the thermocouples. We had 6 thermocouples on each end winding. That's what the TCs stand for. And so that's a total of 12 thermocouples data averaged together. And here are the results. Looks very similar to the results we'd seen before. Honestly, I was expecting maybe 10 or 15 degrees temperature because of the very, very different design of the motor, but we were seeing up to 35 degrees lower temperature at the temperature limit of the unpotted motor. If you calculate that out, it turns out to be a torque that's about 16% higher. And I've got the copper losses shown there at the bottom, but as I mentioned, that would have translated, we thought, into an efficiency, and it turns out that in a lot of motors there are other contributors to the efficiency, and so this thermal benefit, at least in designs we've looked at so far, is not improving efficiency as much as it's improving power density. We published this in IEEE Transactions, and just to kind of show you a prediction from this, since this is a totally enclosed motor, there is no airflow through the motor that would help to cool the rotor. So by having the outer, the stator 35 degrees cooler, we were actually predicting that you would get about a 9-degree decrease in the temperature of the rotor. We didn't measure it at the time, so we don't actually have the comparison data. But in general, I think that's something that you could expect, is that you would see some degree of decrease in temperature also of the rotor. So if you have permanent magnets or you're worried about losses in the rotor, that may be something that would help as well. We have extended this work to epoxies now. As we were speaking with motor manufacturers, the silicones are relatively soft, elastomeric materials. They tend to expand more as you heat them up. And so a lot of motor manufacturers wanted something that was more rigid, had a little bit more mechanical stability. So we were looking into this and trying to think about, well, the current drawbacks of current epoxies is they tend to crack during thermal cycling. So we needed something that was going to be very high temperature stable, and also have a thermal expansion coefficient that would match the metal and copper in the stator. So we developed, in collaboration with our chemical research group, a material, an epoxy material called Cooltherm EP3500. It's a 3.5 watt per meter K epoxy that has a TG of 205 and a thermal expansion coefficient of about 10 parts per million per degree C, which is just about the same as steel. It's relatively thick material, but again, it flows when you warm it up. For epoxies, generally, if you warm them up, you get much lower viscosity. So whereas with the silicone, you pot at room temperature, and then you can warm it up for the cure just to accelerate that. With epoxies, you want everything warm from the start, and then you do an elevated temperature cure after that. What is of note is that this is, the curve you're looking at here is at the 174% torque. So the Cooltherm SC320 would come just a little bit to the left of the EP3500. And if you plotted it, it would fall exactly on that line. So it really is not dependent on the chemistry of the material. It's dependent on the thermal conductivity that you see. We also wanted to see if we could get some data on extending lifetime. And in some ways, this study didn't work out the way we wanted it to, because all of these motors had varnish inside them. And what happened is the varnish itself degraded and got into the rotor gap and caused the rotor to stop turning. And that happened in all of the motors at some point. So we were more looking, what we're seeing more here is the effects of some thermal cycling from room temperature up to very high temperature on the different materials, and the kind of proving just how much thermal benefit you can get. So the way we did this study was we took the same motors that we've been talking about. They were run under very high load, but they were turned on for only about 2.7 seconds, and then they were turned back off. And hundreds of starts per hour were done to cause the inrush current to heat the stator. We're trying to minimize bearing wear and other kinds of failure. We really wanted it to be a true thermal test. And so we would do that, and what's shown on this graph is sort of a typical day's temperature readings. So we would turn it on in the morning, it would rapidly heat up until it stabilized at some temperature. All the motors were run under the same power conditions. We had a reference motor that was the 1.5 watt epoxy that we'll talk about. And that's where we were sort of targeting our temperatures. And then we just let the other motors fall in whatever temperature they were achieved under those conditions. So the temperature cycling was going from room temperature to whatever high temperature, 8 hours at high temperature, overnight, cooling back down to room temperature. We did that for 25 days. The figure here shows the bottom motors are the potted motors and the upper motors are the load motors. So very brief summary. This is published in a white paper that you can get from Lord. So I'm not going to go into a whole lot of detail here, but if you look at the center line, which is kind of blue and green, that's our reference motor. There were actually a couple of different competitor motors that were about 1.2 to 1.4 watts per meter K. And so we chose that as the reference motor. And during the first week, we were setting it at class H conditions for the reference motor. Because as you can see, the red line, which is the unpotted motor, was now running, or I'm sorry, we were targeting class F, but the unpotted motor was running like it was class H. Since it's supposed to be a class F motor, we thought, oh, it's going to fail really quickly, and the test will be done soon. After a week, everything was still running, so the motor was clearly over-designed for the use. So we kept going, and every week we would go up by 20 degrees until we started seeing true failures. And you can see at the end, we're running the reference motors at a target of 220 degrees. And at that temperature, the unpotted motor is running at 240, and our motor is running right at about 200 or maybe even a little bit less. So the higher the temperature of the unpotted motor, the more power you're putting through, the more benefit you get from the high thermal conductivity materials. In the photos down here at the bottom, what you see on the left is the Cooltherm EP3500 after the test. And on the right is one of the competitor epoxies. And the key there is that there are some pretty large radial cracks that occurred due to the thermal cycling of the motor during the 25-day test. We don't see those same kinds of stress cracks in the EP3500. So we think that was a good benefit there as well. We have done some studies also with Siemens here in Germany. They've allowed us to share this, and I gave this similar talk back in February, and I told the people that we're allowed to share this data if we say that Siemens engineers are the greatest in the world. So I just want to be on record that I've actually said the words, just so that you know. It's a very similar kind of study. So we have a motor with a housing, air-cooled from the outside as well. In this case, there was no varnish. So these were motors that had no varnish and that we were simply potting them. Here we use the Cooltherm EP3500 and then an early prototype of a 3-watt epoxy as well, 3.5-watt epoxy. And then we used our Cooltherm SC320 3-watt silicone and a prototype of what is now our 4-watt silicone called Cooltherm SC324. So 4 test motors, 2 silicones, 2 epoxies. Potting process is very similar. We did have a little more challenge getting the material into these motors because it had to flow only through the slots. And the degree to which we filled the slots is uncertain at this point. We know we got the end windings, but how much actually is inside the slots, we haven't done any cross sections to see that. I also include on the picture here, on the right side is the Cooltherm EP3500, the top versus the bottom, because frequently with epoxies, you will get a very, very thin layer right at the surface where it's a resin-rich material. It's usually less than 1 millimeter thick, and it doesn't affect the bulk properties at all. It's a surface energy effect, not so much a settling of the filler material that's inside there. But just to let you know, that's an effect that you will see. So, oh, I'm sorry, I need to finish here. In this test, they ran heat tests at rated power and then up to the thermal limit of the motors, and then measured how much power there was. And then they thermal cycled from minus 60 C, 2.5 hours, up to 200 C, 2.5 hours. And they did that 150 times. Then they repeated the heat test, and that's the data that I'm going to show on the next slide. The upper graph is before thermal cycling, and the black line that you see there on the left-hand side is the 4 kilowatt rated power of the motor, and then you see that the unpotted motor got up to 140 C at about 4.75 watts. All the potted motors are the other lines underneath, and so at the rated power, you see we're about 25, 30 degrees cooler, somewhere in there. And the power that we're getting out of these motors at the thermal limit is 16 to 20% more. So very similar to what we had seen with the other motor tests that we've done. After thermal cycling, the power is almost the same. And it's the one difference is we did not thermal cycle the unpotted motor. So the power that's shown here is compared to an uncycled unpotted motor. We don't know how much loss of power there might have been in the unpotted motor if it had been thermal cycled. So it's a little bit of a not entirely apples to apples comparison, as they say, but we're still seeing a pretty good benefit in terms of the power. This is the condition of the motors after the test, and remember these went through the high thermal cycling. On the left are the epoxy materials, and you can see again there's no radial stress cracks, so even with the very extreme cycling we didn't see any cracks in that direction. However, on the inner board there were some hairline cracks, and you can see that in the bottom middle picture over on that side. That white line is just a very narrow crack, but it didn't affect the performance of the motor. Whether it would affect ingress of chemicals, we don't know. We haven't done that test, and unfortunately, we don't have access to the motors to complete that. On the right-hand side are shown the two silicones, and I use this one to kind of point out this bottom picture here. There's some gray material that's been worn away. Because the silicone expands so much more when it's heated, it impinged on the rotor somewhat. And so that wear area is where it was kind of wearing on the rotor. And you might have noticed in the silicone data, the power is not quite as high, probably because we were robbing some of the power from that. That's one of our key learnings is that if you're going to use a material like this, you need to watch out for thermal expansion. You need to consider thermal expansion of the material when you're designing the mold. We used exactly the same mold for all of these motors, and so for the epoxies it was great, but for the silicones we should have taken account of that when we designed that mold. Another customer case study, I'm not able to share quite as many details, but in this application it was a small motor that was potted inside essentially a tube where there was no possibility for any airflow and it couldn't be liquid cooled. So the only way this motor could be cooled was radiation away from the housing. And so in this motor, the test configurations were no potting, just sort of standard. They also were using a thermally emissive paint on the housing to enhance the heat transfer away from the motor. And that's what's shown in the red line in the middle. So even without potting, improving the heat sink by getting rid of the heat more effectively got you a pretty good improvement in temperature there, 16% more power at 7 degrees lower temperature. If you combine that with potting so that you're now making a very effective thermal connection between the windings and the housing, and then the housing transfers the heat away, you can get 30% more power at 9 degrees lower temperature still. So we never even got to the temperature limit for that. How much more power they could have gotten out at the temperature limit is would need to be assessed. So sort of a summary of all of these different studies. We are typically seeing temperatures 30 to 50 degrees lower when we make that good connection between the windings and the housing. If you have an efficient heat sink, that makes it even better. But even with just a standard fan-cooled motor, you would see some very good improvement. You don't necessarily have to penetrate the windings as well. Just overmolding the outside seems to provide a lot of benefit. And we're not sure. We know that cracks always are upsetting, and we're upset by them too. We'd like to develop something that was crack-free, and we're working on that right now in our next generation development. But we found that they do not necessarily degrade the performance of the motor. So if you're in an application where you're not going to be seeing necessarily a lot of chemical ingress, and so a minor crack in the motor is not a big deal, then you shouldn't see any problems with some minor stress cracks. The problem with epoxies comes in when you get constant expansion and contraction, and now you're breaking big pieces off in little chunks, and that becomes a problem. We know that that's an issue, but we have not seen that kind of issue with the epoxies that we've developed. These two down here at the bottom are just a couple of minor ones. Again, the lower copper losses, if they're important in your application, we do provide that. We have seen that. And that the rotor cooling may be possible, but again, that would need some verification. So in the last few minutes here, I'd like to talk quickly about some of the guidelines that we would recommend when it comes to potting. First is that early in the design process, engage with whoever your material supplier is. We hope it's us, but whoever it is, make sure you talk to them early, because you are motor design experts, but you're not necessarily material experts. We are material experts, but we don't really know anything about motor design. So it needs to be a collaborative discussion during the design so that we can really pick the right material for you. If you need something that's rigid, if you need something that has good chemical resistance for some reason, something that matches the thermal expansion, and that would be epoxies. If you're looking for something that's more, if you've got something that where you don't have those kinds of same constraints, and you want something that's a little bit softer, silicones are a good choice there. They're maybe a little bit better for temperature cycling because they are soft. Up to down to very low temperatures, but that does come with a high thermal expansion that you need to take account of in your design. Just potting a motor that has already been designed, you can sometimes run into troubles. If you design the motor kind of thinking about, I want potting material to be able to penetrate, that can make the process much easier. So ensure that you have good contact with the heat sink. I'll show some pictures on the next slide here. There are cases where the housing of the motor does not extend up to it only is where the lamination stack is. It doesn't extend above the windings. There, you don't really have a good connection to the heatsink at all. And so the thermal transfer is going to be pretty minimal. You really want a motor where that housing extends up, or the jacket extends up above the top of the windings, or at least to the top of the windings, so you can fill in that critical gap. Potting under vacuum, we generally recommend just to ensure that you get rid of any voids that are in the material. Air is a terrible conductor of heat, and any gaps that you create there are a problem. In addition to having the heatsink extend high enough, you also need to make sure that you have good adhesion to that heatsink. In some of our accelerated aging tests, the SC320 motor actually didn't perform as well as we expected. And when we did failure analysis after the test, we found that we had lost the bond at the housing. And just that very narrow air gap was enough to cut the thermal transfer by about 50%. So you need to ensure that you have a good adhesion in that area. Filling from the top is generally an easier process, but there's a couple of caveats there. You've got to make sure that there's some way to get the material from the top to the bottom of the motor. So either you have to have large wire diameters and not tightly packed slots, or you have to have some kind of channel from the top to the bottom. And I'll show a picture of that in a minute. Very similar to what we had in our first motor that we potted. So an easy flow path. If you don't have that, and you want to fill through the windings, and pretty much going through the slots is the only way to fill, we actually recommend that you fill from the bottom and that you fill at a relatively slow rate. Because what you're doing then is you're filling in all of the air gaps, and it's slowly moving up through the slots and expelling any air that's in there. If you fill it too fast, the material will take the path of least resistance but leave a lot of voids behind that then have to backfill from the end windings. And of course, you need to take into account thermal expansion when you're designing the mold. Of the mold material itself, so you want it to expand so that it makes a tight fit, but not an overly tight fit at the potting temperature. And you also want to make sure that you don't do what we did and make a mold that allows the material to expand into the gap. We've actually done that a couple of times, and it's never fun when that happens. You take a motor and you turn it into a resistive heater, and that's really not what you're trying to do. So on the left, it's kind of a summary of what's an easy motor to pot. So you can see there that the housing extends above the windings, and actually on the left and right-hand sides of the second picture, there's a little rectangular channel that goes from the top to the bottom. Extremely easy to fill. We've got a potted version of that little motor in our booth. Come on down, take a look at it. You can fill that motor in 10 minutes using not the most sophisticated equipment and get a really nice fill. The one on the right is not as easy to fill, but you can do it. We have a motor demo running, and the potted motor is this exact motor here. And so you can see what's happening here is that, I'm sorry, I keep pointing at the wrong thing. The end windings are extending out from the housing. There's no good connection there. In this case, the way we potted it, and what you have to do is you have to connect one of the end caps to the motor and essentially pot the motor in a can. That now means you cannot remove the end cap anymore. So you only get to do one side of the motor that way. The other side, it's potted, but there's not really any good connection to the housing. So you don't get as good thermal transfer at that side. But you have to leave one side open so you can assemble the motor. And the finished motor is on the bottom, and you can see it's essentially potted all the way down to the bottom there. Becomes a little more complicated because you've got to make sure you leave the areas for the bearings free as well. So we've considered some other advantages, potential advantages of potting with motors. Not proven in our tests yet, but I think certainly you would expect that these would be additional advantages you could get. First, ruggedizing. So if you're potting the end windings, even if you don't want thermal conductivity, much of the reason to pot a motor is to protect it from the environment, to protect it from vibration, to protect it from chemical ingress or moisture, something like that. The epoxies in particular are going to be good for that kind of potting. With thermally conductive materials, we have universally seen more even distribution of temperature throughout the windings. So not only do you have a lower temperature, but the variation from one place to another is less. And it's the variation, the hot spot, that is going to cause a failure. So if you can minimize that variation and get all of the spots more even temperature, then you're going to have better durability and performance in that case. Because you're filling up all of the air voids with material, there's no air, and so these become nearly explosion-proof type motors. So it's a way to much improve the explosion-proof, the ability to wash down motors, that kind of thing. And we have recently been doing some work. I can't share a lot of the information on it, but a lot of motors for electric vehicles are cooled by direct liquid impinging on the windings themselves. We had always kind of traditionally thought that if you're doing that, potting won't really help you, that potting is an option. But the fact that you can get more even cooling with a potting material has actually been somewhat interesting. So if you have a variation that's this large with a motor that is being liquid cooled, and then you have a variation that's only this large with a potted motor, then even if the average temperature is not quite the same, there still are hot spots in the unpotted motor that could lead to failure sites. So what we're working on right now is trying to figure out how can we combine both of those so that you could provide some kind of potting solution even for a liquid cooled motor of that type. So last slide here, we think that thermal management materials can improve power density for sure. and improve lifetime in your motors. Collaborating with us in the design can maximize that. You know how much thermal conductivity you need. Maybe you don't need a full 3 watts per meter K if you're not going to very high temperature. Maybe a 1.5 watt material is just fine. In that case, it may be a little bit easier to pot. What's the maximum temperature that you're going to be needing to achieve in your motors? And then how do you get it into the motor? What's the best application method? And how do you design the device so that it can accept the material?